Yeah, let's consider the method involving iodine. Iodine is a quite widely used oxidant. Okay, look at let's see. Is standard reduction potential is 0.535 volt. Okay, so iodine I2, this is not strong, very strong oxidant, but the mild oxidant. Okay, so it has more selectivity. So here are there are two types of using iodine. Okay, as an uh, oxidant here, iodimetry and iodometry. Okay, here iodimetry, yeah, is reducing light is directly titrated with iodine. Okay, after the being used, iodine becomes iodide. Okay, but using iodine as an oxidant has a one slight small problem, which is that this iodine, this is solid. Okay, um, it is not very soluble in water. The solubility is 1.3 times 10 to the minus 3 molar, right, at 20 degrees C. Yeah, 1.3 millimolar, right? That's too low. But fortunately, if you add iodide into iodine, and then solubility increases quite a bit. Okay, so it becomes iodide, 3 iodide here, ion. Well, so iodine and 3 iodide, they are different material, but fortunately, they are electrochemically they uh, uh, exactly the same. That the role of this iodide is to simply enhance the solubility. Okay, so actually here iodide in iodide is has no role. Okay, except increasing solution. Okay, this solution. Okay, increasing the solubility. Okay, so writing iodine or writing 3 iodide doesn't matter. Okay? They are exactly the same. Okay? The typical 0.05 molar solution of triiodide for titration is prepared. Okay? It can be done using by dissolving 0.12 mole of potassium iodide and at the same time 0.05 mole iodine in 1 liter water. Okay, here you get that. You add excess of iodide because to completely dissolve this iodine. So this iodide concentration depends on here this iodine. Okay, but remember when using iodine as a titrant, we always mean that we are using a solution if iodine plus excess iodide. Okay, and contrary to iodometry is to use iodine as an oxidizing agent, and and oh, no iodine in iodometry is that you produce iodine, okay, and by oxidizing iodide by adding uh, oxidizing agent. Okay, as a result, iodine is produced. Then this iodine is titrated with standard thiosulfate solution. Okay, so iodimetry is direct direct method. Okay, to analyte, yeah, iodimetry. Mm. And iodometry is indirect method because you have to produce iodine, yeah, from the reaction. Okay, And since iodometry and iodometry involves iodine, okay, so indicator is the starch, right? Starch is used as a indicator. So this, the low concentration of starch, even down to 5 micromolar starch, takes a color. Okay, iodimetry is a starch can be used added at the beginning. Okay, that's important. Um, so when you do the titration and the starch is added, okay, the first drop of triiodide after the equivalence point causes the solution to turn dark blue. Okay, why? So since you uh, added iodine to your analyte solution, and then you titrate your analyte with um, standard iodine or standard 3 iodide solution. Okay, and although you add the iodine solution into the your analyte, there is no color change. Okay, but instantaneously you may see the um, blue color, right? But since before the equivalence point iodine is used up by your analyte, okay, but right after the uh, uh, the equivalence point, and when you add even one drop of the iodine solution, then as already equivalence point is passed, so that iodine or triiodide doesn't does not react with the analyte. Yeah? Then this iodine now reacts combined with starch indicator. So color turns dark blue, yeah? And then you have to stop, right? Yeah. In iodometry, yeah, titration of triiodide, yeah, uh, triiodide is present throughout the titration up to the equivalence point. So you understand, yeah? So by other means, you produce triiodide already, okay, from iodide, right? So triiodide is always there, okay? So such should not be added to such a reaction until immediately before the equivalence point, okay? You understand? So if you add uh, the such indicate, okay, um, at the beginning, and then that dark blue color will remain until the equivalence point. Yeah, so then may confuse you. Yeah? You understand? Yeah? In iodometry, you pick up the the dark blue color the disappear. Okay? So as detected visually by fading of the triiodide, right? So you do not add starch until the immediately the before the equivalence point, and then now when you sense the this is the equivalence point is very near, and then you add okay the starch, and then you do the titration, and then after the triiodide is used up by standard reducing agent like thiosulfate solution, right? And then you pick up the point, the when this dark blue color disappears. Okay, that's the equivalence point and the point. Okay, so if you uh, the add starch indicator too early. Yeah? Then some iodine tends to remain bound to starch particles after the equivalence point. So it is not easy to stop precisely at the equivalence point. Okay, and starch iodine in the complex station is temperature dependent. Okay, at 50 degrees C, the color is only 1/10 of intense as at 25 degrees C. Yeah, so increasing temperature is not wise. Okay, so maximum intensity cooling your solution using ice water. Okay. Okay, but now question is how to standardize this triiodide solution. Yeah, fortunately, there are several good reducing agents like this one, tetraarsenic hexoxide, okay, or this one, sodium thiosulfate. I think this is the most widely used one. Okay. Acidic solution of triiodide is unstable due to the slow oxidation of iodide with air, okay, with oxygen. By this reaction, this iodide is oxidized to triiodide. Okay, so neutral solution oxidation is insignificant in the absence of heat, light, and metal ion. Okay, so it is important to avoid heat, light, or metal ion. Okay, and neutral solution is important. Primary standard grade of this one, arsenic oxide in acidic solution. Yeah, this is in a solid. Okay, and you can buy the very high purity of this arsenic oxide. Okay, and uh, it reacts with water to become arsenic acid. Okay, this one. So this one is can be used as a primary solution, a primary reducing solution. Okay. So how does the reduction goes on? Hmm? This one. So this arsenic acid reacts with triiodide in water, and it gives this one. Yeah, it is oxidized because it is now acting as a reducing agent. After reaction with triiodide, it becomes oxidized. Okay, here this arsenic oxidation state is +3, but here its oxidation state is what, plus 5. Okay, so it is oxidized. Okay, this reaction quantitatively goes, okay, at pH 7 to 8. If to basic, this proportionation of the acid occurs. Okay, okay, so proton concentration should be kept small because K is small. Okay, so pH 7 to 8 is optimal. Okay, all right. Here is excellent way to prepare standard iodide solution. Okay, so far we simply assumed that the iodide solution is made of uh, uh, the iodine and iodide. Yeah, you dissolve iodine, okay, and add iodide to increase solubility. But there is another way to produce, quantitatively produce this triiodide solution. You take this iodate. Yeah? This is potassium iodate. You can have a primary standard grade of this compound, yeah, and you add iodide in strong acidic condition, and then you produce this one. Okay, triiodide. This reaction proceeds quantitatively. Yeah? So this is another way to prepare a standard triiodide solution. Okay, and as I said, this triiodide can be quantified by this thiosulfate as a reducing agent. Okay, this is the very famous reaction. Okay? but the stoichiometry is not 1 to 1 but 1 to 2. Okay, 1 triiodide react with 2 thiosulfate. Okay, and this thiosulfate becomes tetrathionate here. Okay, and here, what's the oxidation state of sulfur here? Yeah, this is reducing agent, and then after the reaction, the sulfur oxidation state increased. Okay, now here oxidation state of this one, sulfur is what? +2. Okay, and here, what's the oxidation state of sulfur here? Of course, this sulfur is different from this one. Okay, because they are in different environment. Okay, but on average, what's the oxidation state of sulfur in tetrathionate? Yeah, you calculate. The answer is 2.5. Okay, yeah, so increased by 0.5. Right. Okay, in basic solution, triiodide disproportionation to iodide, and this one. What's the name for this one? Hypoiodous acid. Okay, which can oxidize thiosulfate to sulfate. Okay, sodium thiosulfate is not pure enough to be primary standard. Okay, instead, thiosulfate is usually standardized by reaction with triiodide prepared from this one, potassium iodate and potassium iodide here. We just saw this reaction. Okay, stable solution of sodium thiosulfate is prepared by dissolving the reagent in high quality reagent grade of this one, sodium thiosulfate. Okay, it is available. Okay, dissolved CO2 makes the solution acidic. Okay, and promotes disproportionation of thiosulfate. Yeah, this one also undergoes disproportionation. Yeah, by this reaction. Okay, this sulfur oxidation state is +2, and it is propionates into two species. Okay, this one biosulfur, bisulfite, and sulfur. This is 0, and what's the oxidation state here? Sulfur is +5, right? Oh no, plus. Let me see. This +1. This is +4. Okay, so total, because the total charge is -1. Okay, so sulfur increased the oxidation state to here 4 and decreased to 0. Okay, that is a disproportionation. Metal ion catalyzes oxidation of sulfate. Okay, here, for example, this copper ion now enhance this reaction. Yeah, this one copper working as what? Catalyst. Okay, so you have to avoid the metal ion, yeah, when you dealing with this thiosulfate. Okay, thiosulfate solution should be stored in the dark. Okay? All right. Here is the analytical applications of iodide. Yeah, reducing agent can be titrated with a standard triiodide solution in the presence of starch indicator until reaching the intense blue color. Yeah, this is iodimetry. Okay. Yeah. So iodimetry determination of vitamin C. Yeah, vitamin C is another name is ascorbic acid. Reacted with quantitatively reacted with triiodide to become dihydroascorbic acid. Okay. Yeah. This list now shows how iodimetric titration is used. Okay. Yeah, there are a lot of the species that to be analyzed. Okay, arsenous, stannous, hydrogen, sulfur dioxide, and this one, hydrogen sulfide, and this one, various metal ions. Okay, cysteine, glutathione, thiogluconic acid, thioglycolic acid, mercaptoethanol, uh, cyanic acid like that. Yeah, there are many species that can be determined by standard iodimetric titration. That means these species can are reacted directly reacted with what iodine, okay, or triiodide. As a result, this one becomes this one, okay, arsenic acid. This is arsenic acid, okay. All right, you take a look at this one. All right. So this iodimetry is a very versatile um, the method to determine these species. Okay. In the meantime, iodometry is also widely used. Okay, as I mentioned, iodometry you first you have to produce iodine, yeah, from iodide by oxidizing iodide by other means, and then produce produced iodine or triiodide is determined by standard reducing agent like thiosulfate. Okay, here is the this also there are a lot of species that can be determined by iodometric titration. For example, chlorine, this gas. Yeah? Then this is also oxidizing agent, so chlorine cannot react with iodine. Okay, so chlorine first react with iodide. As a result, triiodide is produced, and this triiodide is determined by thiosulfate. Okay, that way, hypochlorite acid. Okay, hypochlorous acid now react with iodide. As a result, triiodide is produced. Yeah, all like that. Okay, so this iodometry you need twice. First, you have to produce triiodide, and then produced triiodide is determined by the standard reducing agent. Okay. Okay. This is the end of chapter 15. Yeah. And I selected these problem sets. Okay, and then you solve and upload in the eCampus. Okay.